Yes, hi Shreya.
Shreya, you want to unmute and say hello?
Yeah, hi, both of you.
Hi. I can share my screen, right?
Yeah. So let me just, it's a pleasure to welcome Professor Stefanos Kourtis to our this QIQT 2021. And I was just going through his brief CV. He's from this beautiful city of Athens, Greece. Then PhD and postdoctoral experience in Europe. Postdoc being in Cambridge University. Then moved to this Montreal. Sorry, not Montreal. Canada. Now he's a faculty in Sherbrooke, University of Sherbrooke. Now I was just going through his publications. I found quite a bit of similarity between my work in my early days and his. For example, he has computed Jones polynomial, which in our time came through this Chern-Simons theory, Ed Witten's paper, issue to Chern-Simons theory giving rise to Jones polynomial, for which he got Field Medal. So my thesis was on Chern-Simons theory. Chern-Simons theory has connection with the Hall effect and topology. I see quite a few of his work related to that area. So now these ideas from topology and Cornish matter physics is going towards quantum computation and solving some problems there and vice versa. For example, this quantum computations using tensor network, they're actually basically quantum information theories giving back to Cornish matter systems. So he has his legs in both the sides. So it's a pleasure. So Kourtis, the screen is yours.
Thank you very much, Professor Panigrahi. Thank you for the invitation and for putting together this lovely and very exciting program. Today, I would like to talk to you about, as Professor Panigrahi just mentioned, a tool that had the crossover success. It was invented in the field of condensed matter quantum many-body theory and is now finding application both in quantum information and in other fields as well. And that tool is called tensor networks. And in particular, I'm going to focus on how one can represent classical and quantum computation as tensor networks. And so what this allows us to do is either classically simulate quantum computations as efficiently as possible, but also to enact classical computations that are hard. And I will give you particular examples of these computations. So let me begin with an overview of what I will show you. So I will start with the basics so that everybody's on the same page. So we'll start by discussing what is really a tensor. Then I will introduce tensor networks. I will give pictorial examples, and most of this presentation will be simple, but I will point to interesting references along the way. So whoever is interested to go into more depth can follow these references. Then I will show you how to represent computation in general as a tensor network, and I will use two examples. The first is quantum circuits, and these quantum circuits can be made out of universal gate sets, which means that we can represent any quantum computation as a tensor network. And secondly, I will show you a slightly more esoteric, maybe for some of you, topic, which is model counting, or also called satisfiability counting, and how that can be represented also as a tensor network. And that is important because that is a rather universal set of problems that belong to this category that we can also represent as tensor networks. And then in the end, I will sketch out how tensor network contraction algorithms work. The tensor network contraction is the thing that you actually need to do to perform any simulation or computation with tensor networks. And I will show you how some of the algorithms that we have built work, again, on a high level. And I will point you to references to read if you're interested, and also to code that you can play with. Okay. Let's get started. So what is a tensor? So for those of you who do programming on your computer, a tensor is probably a familiar object under a different name. It is basically a multidimensional array, okay? And if we want to write this mathematically, we would write something that has indices, and these indices run over a set of values. It can take a number of different values, usually discrete. One can define different objects, but here I will be interested in just tensors that have a fixed number of indices, fixed number of dimensions, and each index takes a finite number of discrete values. So here I show this as this T, I, J, K. T is the tensor, I, J, K are the indices. If I fix all the indices, I get one value, which here I call Z, and it is just a complex number. Okay, it could be also a real number, an integer, whatever. Here I just chose this value to be complex. And these I, J, K are indices, each of which takes one of a given number of values. So I takes values from 1, 2, 3 to di, j 1 to dj, k 1 to dk. In this case, we have a rank 3 tensor, meaning this tensor takes 3 indices. If you think of it as an array, you would need to fix these 3 values, these 3 indices to get back the value of the tensor, the entry of this array. Now, in parallel, there is a pictorial representation that we use for tensors, which is this one here that I show on the right, where we have a blob with open legs sticking out. And for each leg is supposed to represent one of the 3 indices of the tensor. Right? So if the tensor is rank 3, I expect to have 3 legs sticking out. Here, these legs are I, J, K. This pictorial representation makes writing down and reasoning about tensor networks easier. So just to give a few more examples, matrix is just a rank 2 tensor. So here I show this as Tij. I have one blob with 2 legs sticking out, I and j. And a vector is just a rank 1 tensor. And in this case, I have just one leg sticking out, 1 index to run over. Okay? Okay, so that's simple. That's tensor. What is now a tensor network? A tensor network is like a to-do list of tensor multiplications that people also call contractions. Okay, and the simplest, or perhaps the second simplest example you can imagine is shown here. The matrix vector multiplication can be written as a very simple tensor network. So here I have this vector W, which is the matrix vector product of the matrix M and the vector V. So MV equals W. Now, if I write this explicitly with indices, I have each component of W written like this: sum over J, Mij, Vj. And graphically, this is represented as shown here on the right. So I have the vector here that is shown as this dot with a single leg sticking out, and the matrix, which has these 2 legs, I and j. And these two dots share a leg. So they share a common index. And it is implied that whenever in a tensor network in this diagrammatic notation, when 2 dots share a leg, this is an index to be summed over. So this is a contraction to be done. And so after we do this contraction, which is basically this sum, we get our new vector, which is this W. Another example is a matrix product. So here I'm showing a product of 3 matrices, D equals ABC. And this can be written again explicitly with indices. So DIL is sum over J and K, where J and K here are common indices of matrices A, B, and C. So sum over J and K, Aij, Bjk, CKL. Graphically, again, this is represented as this really simple tensor network. And now you see I have 2 sums to do. One sum over J, one sum over K. And I can decide to do either one of the 2 first. Okay, so here I have decided to do the sum over J first. So I contract A and B together to get AB. So this common index disappears and I get this new matrix over I and K. And then I choose to contract K after, and I end up with my final matrix. So you see here I have a choice. Whenever I have more than one common indices, more than one shared legs between tensors, I have a choice as to which one to contract first. Okay, so the tensor network itself, when I write it down, is really just the to-do list. It tells me which contractions have to be done so that I get the final object that I'm looking for. But then what is really important to understand is that the order of how I do this contraction really matters. Okay, and so here I wanted to illustrate this with a slightly more complicated example, just to also show you, to build up the complexity of the tensor networks. So here's another tensor network of 4 tensors, A, B, C, D. Here there are, as you can see, all indices are shared. So the outcome of this is what? It's a scalar, right? Because if I contract all shared legs, then there will be no legs sticking out. So it means that my tensor will be just a scalar. Okay, so how could I go about contracting this tensor network? Here's one way. So let's pick A and B first and contract this common index I. So do the summation over I first. Then I will end up with a network that looks like this. So now I could choose to contract the product of A and B that I've gotten up here with C. And so I will get the product ABC to be contracted with D, and then I will get my final answer. So this is one choice. Here's another choice. Here I call them schedules, right? So it's a different way, a different order of going through the to-do list. And so here I contract A and C first. Then I contract AC with B, and then ABC with D to get to again get my result. So notice that no matter how I do this calculation, the end product will be the same if I do my math right. But notice the following difference. So here for this first schedule, after the first step, I have built a tensor of rank 4. Now imagine that these indices, each one has a certain dimension, say D, meaning each index takes one of D values. The size of this object here is D to the 4, right? Now, the largest object that I build in the second schedule is a tensor with 3 legs, right? So here I have D to the cube. If D is large, you can see that this can make a big difference in the performance of your algorithm, your contraction algorithm, okay? So this is why the order of how I contract my tensors really matters. And the way, an analogy you can give is that the tensor network gives you the to-do list. And you can imagine the to-do list is like going to the grocery store and getting a number of items, but it does not tell you how to do it in the fastest way possible. This you have to figure out yourself. Okay, one more example to illustrate this. This is one type of tensor network that really comes up in simulations. This is particularly in cases where people work with matrix product states. I will explain what these are in a bit. So this looks like a ladder, right? So again, I have 2 options. I could start contracting along the rungs of the along the legs of the ladder, in which case I would contract first all these top tensors to get this object here. Or I could contract first along the rungs, in which case I would end up first with this object that I show on the bottom right. So clearly these 2 calculations would scale very differently, right? Because this, in the first schedule, the object that I would end up with after I contract one of the legs fully has a size exponential to the number of legs, okay? Because it's D to the number of legs. Whereas in the second case, the largest object I will build is D to the 4. So this here, we have a dramatic difference. So this one would scale exponentially, the other one would scale polynomial, okay? Now, I wanted to tell you one thing about where tensor networks come from. So they come from condensed matter physics. In particular, one of the papers that introduced many of the ideas that we use today is this paper from 2007, where people introduced tensor network renormalization, as it was called. And so in physics, we are typically interested in systems that sit on a lattice, like spins. You can imagine spins or particles sitting in these positions, and they take one of a few states, and you want to find the ground state energy, or you want to find the ground state of the system. And so what these people said was, let's write the state of the system. Here we imagine a classical system as a tensor network that looks exactly like it has exactly the same geometry of the system. And now what we want to do is coarse grain. Coarse graining is something that is popular in physics due to the renormalization group. Okay, but basically what it means is if you imagine that you have a tensor network that describes, say, the partition function of a classical system, you will pick a neighborhood of the lattice, and you will group it or lump it together. And if you do this, you will end up something like what I show here in the middle. And then the crucial step that they proposed was to trim, quote unquote, these bonds here. So you see, if I do this coarse graining, now I get a lattice that is self-similar to what I had before, but now I have two bonds per side, two bonds between two sides in each pair of sides, okay, neighboring sides. And so again, if I were to iterate this, I would get a tensor that would grow exponentially in size. So the idea here is to try and find a hierarchy of the degrees of freedom shared between these sites, and kind of discard the most irrelevant ones. And this is what I call here trim. And this is why you are allowed to go back to something that looks like what you started with, meaning these bonds are now again single instead of double. So I won't go too much into detail, but for those of you interested, you can go and consult this review here that I really like. This is the basis of algorithms like the density matrix renormalization group that is used with particular success for one-dimensional quantum systems. In the problems that I'm going to discuss, meaning computational problems, this approach typically does not work. So even though tensor networks were introduced to do this thing, this trimming and this coarse graining approximately, from now on, what I will be discussing, we will be doing things exactly. So we will not be trimming anything. And I will get back to why we want this to be exact. Okay, so that is my brief introduction to tensor networks. I can take any questions that you have, if there are any. Let me just quickly mention here, what are tensor networks used for currently? Obviously, we started with quantum many-body physics. So people talked about classical models, people talked about 1D Heisenberg, quantum models, quantum spin models, etc., for which they wanted to find the ground state or the partition function. People then started doing time evolution of quantum systems, etc. Later on, tensor networks found quite a bit of application in data science as sparse representations of data structures. Because instead of if you have some intricately correlated data structure, instead of writing a big array to store all the things that need to be stored in the data structure, you might instead store it in a tensor network in a much more compact way. And so this then led to applications in machine learning, where people nowadays use tensor network representations of their weight matrices and their deep learning models for the sake of efficiency. Because if you can use a sparser representation of your data, you can do your training a lot faster. So this is a very active area of research. And of course, tensor networks have been employed quite a bit in quantum information, both as a theoretical tool to theorize and to say prove bounds, etc., but also as a practical tool for simulation of quantum circuits and other quantum systems. Okay, so I showed you what tensor networks are, and now I would like to show you practically how they look like when you try to actually represent computations as tensor networks. And since this school is on quantum information and quantum technologies, I will start with the thing that you're probably more familiar with, which is quantum computation. So we saw that tensors can represent vectors. Vectors are basically special cases of tensors, matrices as well. So now we can start thinking about quantum mechanics, right, and states in a Hilbert space. So, for example, a qubit is written as a vector in a state. The state of a qubit can be written as a vector in a Hilbert space of two basis states, 0 and 1. And this is what I'm writing here: the state psi of a single qubit as a vector. Okay, so if a vector is a tensor, then I can represent the state as a tensor, as before, right? I have my node here with the leg sticking out that has the single degree of freedom taking two values, and to each I can assign, to each entry, I can assign the coefficients of these two states. So I can represent a state now as a tensor. Moreover, I can look at gates in these Hilbert spaces. They can always be written as matrices. So a single qubit gate is a 2x2 matrix. So this is how I write it here. It acts on a single qubit state, u times psi, gives me another state. But it is basically just a 2x2 matrix. And so I can write it down in my notation as before. I have my node here with two legs sticking out. Okay. And this can be generalized to 2-qubit, any n-qubit gate can be written as a tensor as well. So here what I've done is I take the 2-qubit Hilbert space. So the unitary gate on 2 qubits takes what? Takes the state in the 2-qubit Hilbert space and maps it to another state. Okay, and so this is what I'm showing here. It's just a generalization, and it generalizes to even more qubits than this. Here, I've just chosen to represent these legs individually. And so if I can represent qubit states, I can represent gates, quantum gates as tensors, then I can represent an entire quantum circuit as a tensor network, okay? And so here's an example of this. I'm showing, here's a cartoon of a circuit. This is a brick wall, like 1D circuit, and I'm assuming only 2-qubit gates, but this could be any geometry, like the geometries of the actual quantum chips that you have today. It doesn't really matter, but and here what I've done is I have absorbed any, or contracted rather, any single qubit gates into bigger 2-qubit ones. And so, yeah, I take this 4x4, these 2-qubit matrices, 2-qubit unitaries, and I can reshape them as tensors, and I end up with a structure like this with tensors on a grid, okay? And so why is this important? Well, we know that if I can represent any 1 qubit, any 2 qubit gates, then I can represent really any quantum computation that I want like this. Because if I have arbitrary single qubit rotations and just the C0 gates, then I can represent any quantum computation. And so it means that tensor networks are a language for representing any quantum computation, like a universal language to express them. So how does this look practically? Let's take an example from recent literature. These are some circuits that were introduced in this paper to prove that a quantum computer can perform some tasks faster than a classical one. What exactly they are, it doesn't really matter. Here, what I want to show you is if you take such a circuit, like the circuits in this paper, and you represent it as a tensor network, how does that tensor network look like? And so this is what I'm showing you here. This tensor network at the bottom is an actual circuit, one of those simulated by Google. And you can see that it looks rather random. It looks unstructured, okay? And so you can see here at the outer part of this graph, you see these single leg tensors. These are the initial state or the final state. This is a circuit for a single amplitude, evaluating a single amplitude of the circuit. And so to simulate that quantum circuit or sampling one amplitude of that circuit, I would have to contract this big tensor network, okay? So in the interest of time, I will skip this part, but basically what I want to show here is that you can also represent classical computational problems as tensor network as well. And particularly this problem of counting satisfying assignments for satisfiability problems can be represented as a tensor network. But here we're interested in quantum stuff, so I will skip this. I will very quickly now show you a way to contract unstructured tensor networks. So what I showed you before with the coarse graining was that we have a lattice, and it's easy to coarse grain a lattice, right? You take the neighboring degrees of freedom and you put them together and you just grow the scale. But what happens when a network is, when the system is unstructured? It's like on a random network. So this is what I wanted to illustrate here very briefly for you. You can imagine here that each dot here is a tensor, and the gray circle represents some density of edges everywhere. So everything is connected pretty much to arbitrary range. And because it would look messy, I just represented this as a gray blob. So how would I go about contracting a tensor network that looks like this? So you might naively start from somewhere and contract, say, these two tensors and then keep agglomerating here. But in fact, this turns out to be a very bad strategy. So we would like to keep the tensor sizes as small as possible. So one idea to do this is to kind of try and divide this graph using separators. So you try to cut this big network in half as best you can, such that you cut it roughly in half, but you cut as few bonds as possible. Once you have done this once, then you repeat the process to build this separator hierarchy that I show here. And then once you have done that, then you can start contracting all the neighborhoods, one after the other. Your tensors get bigger and bigger, but you can control their growth by having chosen these cuts to be as short as possible, like meaning these separators. And then in the end, you'll get your result of the simulation or the computation. There are several ways to do this. You can do this exhaustively. Obviously, this takes a very, very long time. And there's a bunch of heuristics that one can come up with. And also one can try to also machine learn part of this optimization. For anybody interested, all these approaches are described in this paper. I don't want to go too much into detail, but Basically, that's how we contract tensor networks. And if you're eager to play with this yourself, there's code online. There's two codes that I was involved with. This is for quantum circuits. There's this QUIMP and Cottengra libraries that also do many other things. This is a professionally written code by my collaborator, and you can find it on GitHub. If you want to look into model counting and this other satisfiability stuff that I skipped over, you can go to this code here that I wrote myself. This is much simpler, much less professionally written, but it is documented. It's well, it works well. But also there are some key players in the quantum field nowadays, quantum information field, that build their own tensor network library. So one example is Tensor Network by Google, and NVIDIA also has recently introduced their own tensor network libraries. So I see that I'm out of time, so I can stop here and take any questions.
If somebody has question, you can unmute yourself and directly ask.
Hello, sir.
Yes.
Is there a difference between the tensors you describe and the tensors we describe in mathematics?
No, not really. I think it is the same thing. The only crucial distinction here is that we always talk about tensors with finite dimensions, finite and discrete dimensions. Okay, so they are like really discrete objects, like a multidimensional array on the computer. Other than that, they are exactly the same thing as defined in mathematics. Yes.
Thank you, sir.
So I see one question in the chat box. I will read it for you.
Okay.
So Rahul has asked, you showed that the quantum circuits can be represented by tensor networks. Can you elaborate on what kind of analysis can be done with them and what advantages it provides over other methods?
Yes, okay, great. This brings me to the part that I didn't have time to go into, but I wanted to show you a bit about performance, right? How do these things work? And so here I took some results from our paper where we simulate the Google circuits on classical computers on a GPU, okay? And so here what I'm showing is, let's forget about, look at the right plot. Here cycles means depth, meaning how many layers of gates you apply. And the y-axis is something proportional to time, simulation time, okay? So the Google estimates for their supremacy claims were based on something that follows roughly the squares here on top, the top curve. Maybe a bit better actually. But what we show is that by carefully choosing your contraction strategy, you can speed this up by many orders of magnitude. And in fact, using these speedups, you can do the simulation that Google initially claimed would take 10,000 years to actually 20 days. And in fact, people have sped this up even further. Okay, so what does this mean? Does this mean that the claim is not valid? No, because it's still a very impressive feat, what they achieved. It's just that the way you contract your tensor networks when you're simulating quantum circuits can have make a very large difference in performance. Okay, so this is the main benefit that you get.
Sir, I have a question.
Yeah.
I want to know what is the role of symmetries in the tensor networks? Like, can symmetries studied in different way by using tensor networks and stuff?
Yes, that's a very interesting domain of research in physics, particularly for physics models studied with tensor networks, because then if you can incorporate symmetries in the way you treat your tensor networks, you can speed up your computations, or you can even simplify your computations even further. I didn't go too much into that. Symmetries do play an important role. I didn't focus on this here because typically when you're talking about computations, if you write a circuit that implements an algorithm, usually the circuit that comes out doesn't have a lot of symmetries. It might have some regularities, but these are hard to exploit in a systematic way. So the answer is yes, symmetries do play a role for tensor networks in general. Translation symmetry, for example, if you're looking at one-dimensional systems where your tensor network is a chain, if you employ translation symmetry, then it means all your tensors must be the same up to a gauge. So it really simplifies computations. But again, for the case of computations represented as tensor networks, this is not as relevant.
Okay, sir. Thank you.
Thank you. Are there other questions?
I have one question. So,
yes, go ahead.
You said that tensor network structure can be used to find certain theoretic bounds in quantum information. So what kind of, I would like to know more about it, and also which properties of these tensor operations allows such bonds to be found?
Yeah, good question. So as mentioned earlier, because tensor networks in a sense are universal language for expressing quantum computation on classical computers, we can reason about the hardness of simulating quantum algorithms or any quantum algorithm classically using tensor networks. So for example, there is a famous paper of almost 20 years old by now, where people showed that any quantum computation that can be represented as a tensor network with a bounded tree width. Tree width is a property of the network, okay? It doesn't really matter, but certain graph theoretic properties hold for the tensor network that represents a quantum computation. When these properties hold, and some of these properties hold, then this quantum computation is actually efficiently simulable on a classical computer. It allows you to make statements like this.
Okay, thank you very much.
The paper that I mentioned is by Markov and Shi, and I think it's 2000. If you follow up with me, I can send you the paper.
Okay, I will look into it. So there is one question in chat. It asks, can tensor network be utilized in continuous variable domain, such as to simulate analog quantum computer?
Yeah, good question. I'm not very familiar with this field. I know that people have used tensor networks to even simulate field theories, where there you really have variables on continuous domains. I know that it exists. I have never used it myself, used these methodologies myself, and I do not know how they work, but I know they do exist. Other questions?
There doesn't seem to be any more questions in the chat box.
Okay. So have we reached the allotted time now, or I thought it was I supposed to go on for longer? I thought it was 30 minutes, right? Or
Yeah, you can go for longer. Yes.
Ah, okay.
Yeah.
There is one more question.
Okay.
So, is there a similarity between tensor network and hidden layers in deep learning?
Yes. In fact, in deep learning, the idea is to represent the hidden layers, each hidden layer as or one of the ideas is that you can represent each hidden layer as a tensor network. What does that save you? Typically, each layer is like a weight matrix, right? So you apply a weight matrix and then you pass to some nonlinear functions. Now, this weight matrix typically is dense. So doing operations on dense matrices is time consuming. Could there be a way to instead replace that dense representation, the dense weight matrix, with a sparse object, like a tensor network? And the answer is yes, but the way to get there is tricky. Apparently, what people are doing nowadays is they first train their network to their neural network to their desired accuracy, and then they try to prune it or to kind of compress it down to a sparser network. Okay, so this is one of the ways that tensor networks are used in that domain, really to represent the hidden layer weight matrices.
So another question is, in TensorFlow, what exactly bias and variance are?
In TensorFlow. Okay, I don't know how to answer this question. Sorry, I think it's a specific library. Is this what this is about? Yeah, sorry, I don't know. I think it's now machine learning, more related to machine learning.
Okay, so there is one more question. Can we use tensor network to improve the time taken in executing quantum key distribution algorithms?
I don't know. Yeah. I don't know at all the answer to this question. Maybe, if you have any ideas, let me know. Sounds interesting.
Yeah. So one very generic question: what is the physical meaning of tensor product and vector cross product? And
yeah. Yeah, good. It can be several things. So if I go back, to this picture, what does it mean to start with an initial state like this psi? You can imagine a product state with little dots here at the beginning of the circuit, right? And then you can imagine the first layer of gates. And now imagine that you contract the full first layer of gates to this initial state. So you do a contraction, right? So you do basically just a summation of indices and matrix multiplications, etc., and that's it. But physically, what has happened? What has happened is that your state has evolved from initial time to the first time step. Okay, so here the physical meaning of contraction is time evolution. Now, you might say, well, what if I don't contract? What if I don't contract in this order, where I apply, say, just the first layer? I contract in some weird order, right? What does this mean physically? This, as a physical meaning, is probably less related to the way we experience and we treat time and space, but it is some evolution in some space-time, right? And that evolution can even be non-unitary, right? So I could one thing that I can mention here is that I could even put non-unitary within a unitary circuit. I can put non-unitary elements also, right? I could put, say, a projector somewhere to say whatever happens, this qubit after this point is going to be projected to zero, to the state zero. So the physical meaning of contraction is generic evolution in some spacetime, right? In more particular cases where you follow some physical process, then you can tie it directly to some physics, but it doesn't need to be so. Okay, and perhaps here I can show you a bit these satisfiability problems, right? So you have Boolean variables, these xi variables, they take values 0 and 1. That's it. These can be represented as tensors. I've written this here as a 3-leg tensor just because I want to copy the same variable to 3 legs because I want to pass it to 3 different interactions. So it's just a Kronecker delta. Tijk is this Kronecker tensor. And then I have clauses. And clauses are basically Boolean operations on tuples or like set groups of these variables. So here, this clause CM is XP or XQ or XR. And can also be written as a tensor, something where you put in a 1 when XP or XQ or XR is true. Otherwise, you put a 0. And then you can write a Boolean formula like this, which is a conjunction of many such clauses. So these clauses have ORs in them, and now you take a big AND. So you want them to be all valid simultaneously. And so you want to count how many assignments of these Boolean variables satisfy such a formula. And this is called the satisfiability problem or model counting. Okay, and it looks again like a tensor network based on this translation. You use the same language, and now in this space, it is you contract again. It's some evolution, but in the space defined by this formula. Okay, so it's a bit more. It can be a bit more abstract. So in physics, it is you can follow space or time or space-time, but in general, it's just some dynamics. This coarse graining dynamics that happens in some arbitrary space defined by the network.
Yeah,
it's a bit long answer because I wanted to incorporate also this. Yeah.
Yeah, hi, this is Anuj here. So you mentioned in one of the, I think, following slide about the like algorithms, bad algorithms, I think, for the ordering. So could you specify which are the most effective as of date, which are the most effective algorithms for tensor network contraction?
Yeah. So usually at this point, I forgot I had left this bad thing there. So I would make a joke at this part of this presentation. And the bottom line is that all these algorithms are bad, depending on your definition of bad. So what do I mean by this? So we know that there are computations that, for example, the satisfiability problem that I showed you, unless P equals NP, that computation should take exponential time. Okay. Similarly, we know that in the worst case, simulating quantum algorithms will take exponential time unless some rather unlikely collapse happens in the computational complexity hierarchy. Okay. So what does this mean? It means that for example, the simulations that I showed you for the Google circuit, they will by definition take exponential time unless they are either they do some very crude approximation or something really breaks in our understanding of complexity theory. So all these contraction algorithms will lead to a contraction that takes exponential time. Okay, this is why I call them bad. But my point was that here all these scale exponentially, but if you look at the difference here, you see something like 9 orders of magnitude in performance, right? So this is what I mean that that these algorithms are bad, but which one you choose might be very significant. In particular, to your question regarding which ones seem to be the best so far, we find that algorithms based on this cartoon picture that I showed you here, which is called graph partitioning, seem to work best. So in fact, we go one step further and we do something called hypergraph partitioning, but it doesn't really matter. Basically, the idea is what I showed you here. So basically, you start with whatever structure is your tensor network. Maybe let's look at the particular example, even this guy, okay? So this is your circuit represented as a tensor network. And now you ask, how can I cut this in half in such a way? But cut in half means roughly bisect the tensors such that I have equal numbers of tensors on either side of the partition. So that's what means cut in half, right? So I want to cut in half. Of course, you would say, well, okay, just cut in half. But I want to cut in half such that I cut as few bonds between tensors as possible. Now, what does this achieve? What it says is that if your contraction reaches this point where you just have 2 tensors left, these 2 tensors will have as small a size as possible, because the size of the tensor has to do with how many legs are sticking out of the tensor. Now, you do this one time, and then you do this iteratively. This is the cartoon picture here, right? So I do the first cut such that it minimizes the number of legs shared between the 2 sides of the partition. And then for each half, I do the same thing iteratively, all the way down until I get to the individual tensor level. And then once I have done that, now I can contract back up, right? And having done this graph partitioning in a somewhat clever way, tells me that these tensors that I get as I contract, as I go along in my contraction sequence, will be as small as possible at every step. So this is the strategy that we find yields the better results that we get so far. Of course, this is problem dependent. We know it works well for random graphs. We know it works well for random circuits. But the next question for the future is there a particular contraction strategy that is best suited to a particular quantum algorithm that I want to simulate, or a particular type of quantum circuits? And that is totally open. Yeah.
Thank you. Thanks for the explanation. Thank you.
Sure. Thanks.
There is one more question. Sarang has asked, when it comes to open quantum systems, one encounters many noises as a consequence of interaction of system with environment. So can tensor network simulate such a noises?
Yeah. Also a good question. So this, for this, I wanted to tell you one thing that is going on currently in my group. One thing that we are really interested in nowadays is doing contractions approximately in the cases where this can work. Going back to the quantum circuit case, you can show and you can convince yourself that if at some point you do this trimming, when you try to contract, say, the Google circuits, right? These are chosen because they are scrambling. They have some dynamics that people call scrambling. They are basically very hard to simulate. And hard to simulate means that if I try to do an approximation at any point, that approximation is probably uncontrollable. So if I say, well, this is small, I can discard it. Like you have a gate and you say, well, these entries in the matrix of the gate, these are small, let me ignore them. Now these entries might play a very important role further down the road. So you cannot ignore anything. Now, in contrast, there are other systems for which you can safely discard part of the information, such as the circuits, the systems that I showed you in physics that people did the trimming earlier in the early days of tensor networks. Now, another case where this seems to work well is quantum error correction. So there, one way to, I don't want to explain to you fully what quantum error correction is, but basically is you pass your information through a channel. That channel is noisy and kind of disturbs your information. And then you get the output and you want to recover the input from the output. So you first encode, instead of just sending your information through, you encode it in a redundant space, like in a bigger space, such that you can detect and correct errors, okay? And so this is very much like an open system. And what you ask is, can I recover the information? Or can I correct the message that I got, the quantum state that I got, to go back to the manifold of states that I started with. And this is in fact what we're working on in our group, because in this case, you can do approximate contractions. Precisely because of the fact that you have noise and you care just about the most likely state and not the exact state. So in other words, maybe one way I could put this is, imagine that instead of requiring to recover a full quantum state, you just want to recover the component with the largest amplitude. It's a much easier problem, right? So this is why approximate methods seem to work in this case. So yeah, you can treat open systems for sure.
Thank you, sir, for the answer.
Yeah, Stefano, I have a question. I saw in one of your paper, this Jones polynomial computation. Can you elaborate a little more on that? How did you attempt that problem?
Yeah, definitely, I can do that. So I even have it here as in the conclusion slide. I didn't mention it, but basically, if you can do counting of satisfiability problems, you can basically do counting of any classical partition function of any statistical mechanical model you want. Now, what the problem that Professor Panigrahi is referring to is the Jones polynomial. It's the evaluation of an invariant of knots. Knots are these, you know what knots are. You tie your shoes or you take your earphones out of your pocket and they're like messed up in this jumble, and then you see how hard it is to untangle them, right? So it is also hard to evaluate invariants of these knots. Basically, these are invariants that characterize, you hope that they characterize this knot uniquely, right? Because there are operations. So if I do a twist I grab, say, a string and I do just a simple twist, that doesn't really change the topologically the knot. The knot is either knotted or unknotted, regardless of whether I grab it somewhere and do a twist. So an invariant should not change based on like trivial moves, right? So calculating these invariants boils down to evaluating partition functions of classical StatMech models, like Potts models, with funky properties. So they have like a site-dependent temperature, and they have a particular form. So basically, you take your knot, you put it on a plane on the table, say, and then you discretize it by looking at all the crossings, if they're above or below, etc., which string is above or below, and then there's a standard way of mapping those knots and their evaluation of their polynomial or their invariant polynomials as StatMech models. And if you do that mapping, then you can do the next mapping, which is the StatMech model to a tensor network evaluation. And so in this paper with my collaborator, what we did was we evaluated for arbitrary knots their Jones polynomial. So this is, again, a computationally hard problem, right? So there, again, our algorithms scaled. There, they scaled better than exponentially, precisely because knots are planar objects. You can always write them as a diagram on the plane with just one string going above or below the other. And yeah, what we found in that paper is, again, tensor networks perform really well. They can evaluate these otherwise hard to evaluate polynomials or knot invariants in a much more efficient way.
Thank you.
Sure.
Are there any more questions?
I don't see any more questions in the chat box.
Okay, so let's thank Stefan. Very beautiful talk, very enjoyable talk. Thanks a lot.
Thank you very much for having me and for the really fun discussion. If there are any other questions, please reach out to me.
Okay, sure. So thank you and have a good day.
Thank you. You too. Bye-bye.